When we look at heavy industrial machinery, the immediate impression is one of brute physical force. But if you watch closely, that raw mechanical muscle is capable of stopping entirely on command, down to the millimeter. Hydraulic circuitry provides this control through a programmable, analog logic system. Instead of routing electricity through wires to process commands, engineers route pressurized oil through rigid pathways to dictate complex physical behaviors. To read these analog computers, we use the standardized ISO 1219 visual language. This chart outlines the basic directional control valves. You'll see port designations like P for pressure input, T for tank return, and A and B for power ports. Shifting these internal configurations changes the fluid path, acting as foundational logic gates. To understand how industrial machinery works, you have to decode the specific taxonomy of these foundational subcircuits. We are going to map out exactly 9 specific fluid architectures that form the backbone of modern automated machinery. By isolating each of these designs, we can see exactly how engineers translate mathematical pressure into strictly controlled motion. Every hydraulic system requires a prime mover to generate flow. This is the hydraulic power pack. An electric motor drives a fixed displacement pump, pulling oil from the reservoir and pushing a continuous flow outward into the circuit. But you cannot simply pump raw oil. We have to introduce our first sub-architecture, the filtration circuit. These systems require capturing particulate matter as small as 0.06 to 0.1 millimeters. If those particles bypass the filter, they will physically erode the tight internal tolerances of the pump. This creates an immediate engineering trade-off. As the filter traps dirt, the fluid faces more resistance. A high degree of filter contamination causes a severe pressure drop right at the intake, which will literally starve the pump of fluid. Once we have clean, moving fluid, we have to address the risk of structural failure. If the fluid hits a dead end, pressure will rise infinitely until a pipe bursts. That brings us to the pressure control circuit. When the flow encounters too much resistance, a pressure relief valve physically pushes open and throttles the excess fluid directly back into the reservoir. This establishes a state of equilibrium. The valve enforces a strict limit, capping the maximum allowable pressure in the entire system, no matter what happens downstream. Power generation, microscopic filtration, and hard pressure relief are the mandatory baseline architectures. Without them, any complex fluid logic would instantly tear itself apart. Moving beyond the baseline, engineers have to deal with parasitic drag. Running a pump at maximum output against a cylinder that is already fully extended wastes a massive amount of electrical energy and converts that wasted work entirely into destructive heat. To solve this, we use the unload circuit. This architecture uses 2 separate pumps. One provides high pressure at a small volume, the other provides low pressure at a large volume. When the system hits its pressure limit, like when a press reaches the bottom of its stroke, pilot pressure forces an unloading valve open. This bypasses the large volume flow harmlessly back into the tank, stripping away the energy waste. The system naturally resets itself. When the machine reverses and the cylinder retracts, the pressure in the pilot line drops. The unloading valve snaps shut, and the system restores the full combined output of both pumps for rapid movement. Sometimes the problem is the exact opposite. Instead of the motor driving the cylinder, an external kinetic force, like gravity acting on a heavy crane load, pulls down on the cylinder, forcing oil through the system backward. To manage this, we rely on the brake circuit. By restricting the exit flow, the system effectively reverses its function. The hydraulic pump acts as a hydraulic motor, absorbing the kinetic power to smoothly decelerate the descending weight. Advanced fluid power requires managing and safely diverting kinetic energy with the exact same precision used to generate pushing force. Controlling the exact speed of a machine element is entirely dependent on regulating the rate of the liquid flow. This diagram outlines the speed change circuit, which shifts a machine from rapid transit into a slow, highly controlled working pace. Notice the directional control valves operated by 3 solenoids, labeled SOL1, SOL2, and SOL3. By switching the states of these solenoids, the circuit dictates exactly where the fluid goes. It routes the oil specifically through the large flow rate restrictor for fast movement, and then seamlessly diverts it to the small flow rate restrictor to slow the cylinder down right before making contact. These fixed restrictors are simple, but they have an inherent operational weakness. The actual flow rate will fluctuate if the fluid's viscosity changes, or if the pressure differential between the inlet and outlet shifts. They work best when operating conditions remain completely stable. But what happens when you introduce multi-axis movement? Imagine lifting a single massive platform using 2 separate hydraulic cylinders. If one cylinder extends even slightly faster than the other, the platform tilts, binds, and destroys the machine. This is the synchronizing circuit. In this specific schematic, you can see the rods of the main cylinders and the auxiliary cylinders are mechanically linked together to force a synchronized motion. Even with a mechanical link, microscopic synchronization errors happen due to manufacturing tolerances. The strict design rule here is that the circuit must force any accumulated error to correct itself at the absolute end of a full cylinder stroke, rather than attempting to fix it halfway through a motion. Alternatively, some systems ditch the mechanical linkage and use synchronized hydraulic motors instead. Those systems rely entirely on each motor possessing the exact same volumetric efficiency to displace identical amounts of fluid. Perfecting flow diversion and preventing synchronization drift is what separates a crude lifting device from a modern, automated manufacturing line. There is a hard physical limit to the pressure a standard shop compressor can output. But applications like water jet cutting require pressures that far exceed those standard limits. For that, we use the intensifying circuit. This relies on a core physics principle, multiplying pressure by using the geometric ratio between two different cylinder cross-sections. Low-pressure fluid pushes against a large piston, which is physically locked to a much smaller piston. Because the surface area of the second piston is smaller, the pressure of the fluid it pushes is multiplied. By using cross-section ratios of 1 to 10 or 1 to 25, this architecture can safely output up to 400 megapascals. But the physics exact a toll. At these extreme pressures, water actually compresses. The first 15% of the intensifier stroke is completely wasted just physically compressing the fluid before a single drop of volume is delivered to the cutting head. The final architecture uses fluid to deliver continuous, gearless movement to heavy vehicles. Up to now, we've looked at open circuits that pull fluid from a large reservoir. Hydrostatic transmissions, or HSTs, operate as a closed-circuit topology. The fluid loops continuously between the pump and the actuator without dumping into a tank. This allows a single hydraulic pump to directly control the speed, braking, and reverse functions of a hydraulic motor located right on a vehicle's axle. It completely eliminates the need for a mechanical shift-change gearbox. Whether they are amplifying force by a factor of 25 or removing complex physical drivetrains entirely, these designs prove the scalability of fluid power. We have mapped power generation, efficiency management, synchronized actuation, and extreme pressure scaling. The fluid dynamics dictating these 9 architectures are completely immutable, but the methods engineers use to control them are undergoing a severe shift. Designers are currently integrating electronics directly into fluid pathways. Purely mechanical springs and fixed throttles are being replaced by proportional digital valves. Modern machinery utilizes embedded IoT pressure sensors to monitor fluid behavior in real time. Instead of waiting for a cylinder to finish its stroke to correction a synchronization error, digital controllers predict and adjust the valve positions dynamically, mid-movement. Heavy industry will always rely on the brute, unyielding force of pressurized fluid, but moving forward, that power will only be as effective as the digital logic instructing it.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.